let's talk about the laws of probability. One way to start off is with a statement: there is this thing called probability. It's a mathematical thing. It obeys the laws of an axiomatic system. But interestingly, it can also be identified with the real world. And when you make that identification, it gives partial information about the future. That's what makes it useful, and that's the power of applying probability to this field that we're going to call statistics. The first question raised by the above statement is, which axiomatic system is it that we're going to call probability? It turns out there's only one good answer to that. Everybody agrees. But the second question that we've raised, how do we make this identification to the real world, that actually doesn't have a single unique answer. In fact, over the course of the 20th century, two different ways of identifying probability to the real world were fought over by two groups of people, one called the Bayesians and the other called the frequentists. Their viewpoints are somewhat different, but they both use the same laws of probability. They just think about how to apply them to the real world in a different way. The interesting thing is that both are useful. In the end, neither the Bayesians nor the frequentists completely won the battle. The Bayesians, however, go farther than the first statement above the statement right here. The Bayesians add that used properly, probability theory gives a consistent and complete calculus of inference. What does that mean, calculus of inference? That means you're given data about the real world and you want to know what conclusions can reasonably be drawn. And you might think that that's a matter of opinion, that different people could simply draw each to them their own valid conclusions. But it turns out that in a certain context, there's only one way to do it, and it is the Bayesian way. At least that's the Bayesian viewpoint of what's going on. We'll see that this viewpoint is kind of true in many ways and maybe not quite true in some other ways. But to give you an idea that there's actually some math behind this, even though we're not going to go into it, the foundational paper on this goes back to 1946 by R.T. Cox. And R.T. Cox showed that if you start off wanting to make reasonable statements about degree of belief in something, that if you make reasonable assumptions, in fact the three assumptions that we're going to go through right here, you end up with the axioms of probability and with the Bayesian viewpoint. So Cox's three reasonable assumptions were, first, that if I believe more in a proposition's negation, that something is not true, then I should believe less in the proposition itself. In other words, the negation and the proposition should move in opposite directions with degree of belief in the one or the other. The second reasonable assumption that Cox introduced was that belief should be composable. If I believe in A and B, and note we're going to just use the concatenation or product notation when we mean and, my belief in A and B should depend only on whether I believe in A, and if A is true, what is my degree of belief in B? In other words, once I believe in A, I don't have to consider the case of whether B is true in the negation of A. The third point is that the belief in a proposition should be independent of the order in which supporting evidence is adduced. In other words, if data set D1 supports a belief to some extent and data set D2 also supports that belief, I should end up in the same place whether I see D1 first or D2 first. Well, let's get back to what are the axioms of probability. We're not really going to be proving theorems in this course, but to give you the idea that there really is mathematics behind this, I think I should at least write them down. And these have the character of set theory, or more accurately, measure theory on sets, which is exactly what they are. So the first axiom just says that any event set A has some probability, written P of A, which is greater or equal to 0. That's reasonable. The second axiom says there's some set omega, which is the set of all possible outcomes. And that exhaustive set of all outcomes should have probability 1. Okay, again, that sounds intuitively reasonable in light of what we mean by probability. The third axiom is slightly more technical. It says, suppose we have two outcomes or two sets of outcomes that don't overlap, so that A intersection B is the null set. Then, if we want to evaluate the probability of A or B, that is, of the union set of outcomes A with outcomes B, we can do that by just adding up the separate probabilities, the probability of A plus the probability of B. We'll see how to get the probability of a union set later in the case where we don't have this assumption, but when we do have this assumption, it's one of the axioms. So if we were really going to go down this road and prove theorems, we'd do things like this. I mean, here's a completely trivial theorem, but just to show you that it follows from the axioms. The theorem says the probability of the null set is 0. You'll notice that we didn't introduce that as one of the axioms, so we have to prove it. Okay, the proof is take any old set A, and A intersected with the null set is the null set. That's simply a property of sets. So therefore, we can come up and use this axiom number 3 here to get the result that the probability of A, which is trivially equal to the probability of A union the null set, because that's simply A. But now, by the axiom above, we have this condition, so we can just add up the probabilities, probability of A plus probability of null set. Now look, we have probability of A on both sides of the equation, and therefore the probability of the null set is 0. Okay, if you like this kind of stuff, you're probably in the wrong course here, because we're not going to be doing much theorem proving in this way. Now what's basically going on is that these axioms are the axioms of a theory of measure on Venn diagrams. So I'm now going to informally prove a bunch of elementary theorems, but we're going to use them in calculations just by looking at the Venn diagrams and seeing what has to be true. So let's start with the law of ORing, is what I call it, because it tells you how to compute the probability of A or B, as we mentioned above. More formally, in real life, this is called the law of additivity. The situation is we have some outcome or set of outcomes A, and we have another set of outcomes B, and we want to know the probability of lying anywhere in this region of A or B. Well, you can see from the picture that we add up the probability of A, which is the yellow shaded region here, and we add up the probability of B, which is the blue shaded region. But when we do that, we've added this overlap region twice. So we have to subtract it off to get the area enclosed by the union of these two sets. And that's written right here, minus the probability of A and B. Again, the notation is concatenation means and. Well, that's easy enough. Here's another one that goes by the name of the Law of Exhaustion, not in the sense of the gentleman up here in this cartoon, but in the sense that if the outcome space omega is divided up into a set of exhaustive and mutually exclusive alternatives R, then the sum of the probability of all those alternatives must be 1, obviously because they add up to the set of all possible outcomes. So it's important to learn this abbreviation, EME, because we're going to use it a lot, exhaustive and mutually exclusive. Exhaustive means that the outcomes completely fill the R's, I should say, completely fill the outcome space, and mutually exclusive means there's no point that is in more than one such outcome. So that's the law of exhaustion. What about the rule that's called the multiplicative rule? I call it the law of anding because it simply gives the formula for computing the and of two things here. Okay, so we want to know what is a formula that we can use to get the area of the green region here, the area of overlap between A and B. Now, if you think about it, the probability of the overlap region is a product of two factors. It's what fraction of omega lies in A, so that's P of A here. And then it's multiplied by what fraction of A is in the overlap. And we write that as the probability of B given A. So the vertical bar is always going to be read as given. And clearly, if this is a certain fraction of omega and this is a certain fraction of A, then the green region is the product of those two numbers as a fraction of omega. Now, I could have done the argument completely the other way around using B everywhere instead of A, and then I would have gotten this form of the multiplicative rule. If you think about it for a minute, you'll see that this isn't really a theorem at all. It's really a definition of conditional probability. And simply rewriting it, dividing this equation by P of A, you'll see that what we're really writing down is that the conditional probability of B given A is, in the numerator, the probability of A and B, that is to say the green region, and in the denominator, the probability of A, that is to say the yellow region in this picture. So one way to think about this is that whenever we have a conditional on this side of a vertical bar, that means that we have to renormalize the outcome space because our new outcome space is not all of omega but only A, and so we have a P of A in the denominator. If that's not immediately obvious, you might pause the recording and think about it at this point. You can apply the law of anding several times to an expression and sort of peel off the pieces. And you can do this in any order because A and B and C is commutative and associative on any order of the A, B, and C. So, for example, the probability of A and B and C is the probability of A, and then the probability of B given A, and then the probability of C given both A and B. And you can see that this is true either by algebraically applying the previous formula, or I suppose you could draw a Venn diagram and see what each fraction of the previous one is being multiplied together. There's another concept called the concept of independence that we can cover here on this same slide. Events A and B are said to be independent if the probability of A given B is the same as the unconditioned probability of A. In other words, knowing that we're in B has not changed the probability of A from its value as a fraction of the whole outcome space of omega. One way you can draw it, just this is really more to help you remember it than to be mathematically useful, is it says that A is independent of B if A divides up the outcome space into what I've drawn here as vertical bars, and B divides up the outcome space here into horizontal bars, because then you see the fraction of A in the whole space is the same as the fraction of A that's in B, which is just another way of saying this thing up here. Now, when A and B are independent, we get this useful result. We can compute the probability of A and B, okay? And now, by the law of conditional probabilities, that's the probability of B times the probability of A given B. That's essentially from the definition of what given means. But now if the events are independent, we have up here the probability of A given B is equal to the probability of A, and so you see that the probability of A and B just is the product of their separate probabilities. And that's what we mean to say that two events are independent, that their joint probability is simply the product of their individual probabilities. Okay, let's work a problem now. First, let's start with a completely trivial problem. A symmetric die has 6 faces. What is the probability that when I throw it, it will come up one of those faces? Say the probability of 1. Well, the answer for all of them is that it has to be 1/6. Well, that's pretty obvious. Now, why is that true? It's true because we said up here that the die is symmetric, so all the probabilities are the same, and there are 6 of them, and they have to add up to 1 because of the law of exhaustion, that EME events, exhaustive and mutually exclusive events, must have probabilities adding up to 1. Now, notice that I never had to introduce into this argument any kinds of words that say the frequency of occurrence in n trials, that, or if I threw the die many times, it would approach a fraction 1/6 or anything like that. We just don't need that machinery. That will come later to some extent. Let's do a slightly less trivial problem. The sum of the faces of 2 dice that are thrown, a red and a green die. Here we have red and green, except I didn't get the colors right. The sum of their faces is greater than 8. What's the probability that the red face is a 4? How do we think about that? We think about what is the outcome space. The outcome space is every possibility equally probable for the red dice, 1 through 6, and every possibility 1 through 6 for the green die. And now let's do this algebraically by using the laws we have. We'll have to invent a little bit of notation here just for this problem. We'll never see it again. So what we want to calculate, the problem asks us, what is the probability of a red 4 given this condition that the sum of the 2 is greater than 8? So by the definition of conditional probability, that's the probability of the red 4 and greater than 8 divided by the, we called it renormalized outcome space, the probability of it being greater than 8. Now to see what each of these numerator and denominator are, we might as well just go back to the picture. The probability of red 4, that means we're in this column, and sum greater than 8, that's these yellow triangular, staircase region here in the lower right. Okay, so the intersection of the column number 4 with this staircase region where red plus green add up to greater than 8 is just these 2 squares. And therefore the numerator is 2 divided by 36. 36 is the total number of squares up here, of course. The denominator is just the number of squares that I've been outlining here in this staircase yellow region. And if you count them up, you'll see that's 10 out of 36. So the answer to this question is 2/10 or 0.2. One more theorem or law in probability that we're going to use a lot is called the Law of Total Probability. I actually call it the Law of de-anding. You'll see why in a minute. Now, this formula applies when you have a set of exhaustive and mutually exclusive alternatives. So here they're called the H's. Previously we saw a set called the R's. Okay, and then there's some event or event set B that you're interested in, and we're interested in calculating the probability of B. And the theorem is that the probability of B can be broken up into pieces. The piece of B that's in H2, the piece of B that's in H3, the piece of B that's in H4, the piece of B that's in H5, and that if we add up these pieces, or with some notation, write it this way, we get back the probability of B. The other useful form of this is to just convert this probability of B and H sub I by using the law of conditional probabilities. And then we get this form that the probability of B is a sum over EME alternatives, with each one contributing its probability, of the conditional probability of B given that alternative. So the probability of B can be made up of the conditional probabilities of B over a set of EME alternatives times the probability of each alternative. In some sense, this tells you that if you have a set of probabilities that have been taken apart, how to put them back together again. So I think of it as how to put Humpty Dumpty back together again in probability space. Let's do a more complicated example. Suppose that a barrel has in it 3 minnows and 2 trout. And we're going to reach into the barrel and catch a fish, and that seems unlikely, but for whatever reason, we have an equal probability of catching any fish in the barrel. Now the rule is minnows have to be thrown back into the barrel, but trout we keep. And the question we're asked is, what is the probability that the second fish caught is a trout? You might pause the tape and just think about this for a minute, because sometimes you get the idea that all probability questions are trivial and just by pure thought without any calculation you can get the answer. Possibly you can on this one. Why don't you give it a try? Okay, let's go on and see how to do it. We're going to exercise this idea of EME hypotheses here, and there are going to be 2 hypotheses depending on what happens on the first fish. So hypothesis 1 is that the first fish caught is a minnow. Now if you look at the picture over here, you'll see that if we catch a minnow, that's one of these, then we throw it back, and therefore after we've done this, we're left once again with 3 minnows and 2 trouts. The second hypothesis is that the first fish caught is a trout. Now we don't throw it back, so what's left in the barrel is 3 minnows plus only 1 trout. And now the event we're interested in is B, which is the idea that the event of the second fish caught being a trout. So now we simply compute with the law of de-anding. The probability of B is the conditional probability of B given H1 times the probability of H1. Well, let's work that out. Okay, the probability of H1 is the probability that the first fish caught is a minnow, and that's 3/5 because there were 3 minnow and 2 trout. Once that's happened, the probability of B given H1 is the probability of catching a trout in this situation, and that's 2/5. So we multiply that. Now let's go over to the second term here. The other of the H probabilities, H2, is the probability of catching a trout on the first catch, and that must be 2/5, because this one is 3/5, or we can go back and look at the picture of the fish to figure it out. But now what is the probability of catching the trout on the second one, given that the first one caught was a trout? So that means we're in this situation, and the probability of catching a trout is 1/4. So we do the math, and this comes out 0.34 as being the probability that the second fish caught is a trout. Aha, we've calculated something that maybe we couldn't have intuited as a result. Now, just to give you a preview of the kind of question that by the end of this course you're going to be able to answer, I hope easily. Suppose somebody comes along and says, well, maybe the assumptions were wrong, but I have a barrel just like that, and when I do this experiment, I catch a trout the second time exactly 1/3 of the time. 1/3 seems very close to the answer that we got, 0.34. By the way, if you work this out, it's exactly 0.34. How many times would you have to do this experiment in order to prove your friend wrong, to prove that the probability really was 0.34 and not 0.333333? Would you have to do the experiment about 100 times, about 1,000 times, about 1,000,000 times? I'll let you think about that question, and maybe we'll answer it much later in the course.